Someone throws a negatively charged golf ball into space where it interacts with a circular charged plane. The golf ball ends up perfectly centered and very close to the charged plane. If the plane has a surface charge density of 0.56 coulombs per meter squared, determine the electric field present at the location of the golf ball and describe the motion of the golf ball assuming it is no longer moving due to the initial throw. Be sure to address the forces acting on the golf ball at this point. It's also important to note that the total charge is 50 coulombs. So the first thing you want to do when you're doing a problem like this is make sure that you work through the problem conceptually before you try and plug in a whole bunch of numbers and do it mathematically. So that's what I've done here. I have the electric field due to the ring is equal to 1 over 4 pi epsilon naught times delta q z over r squared plus c squared to the 3/2 times this 0, 0, 1 unit vector. The reason why we have this oriented in the z direction like so is because this plane is oriented in the xy direction as shown here in the photo, and because of this we only expect a contribution of the electric field in the z hat direction, which is perpendicular to the xy. From there we see that we need this delta q, so from there we get delta q is equal to big Q times 2 pi r delta r over pi big R squared, where the big R is the radius of the entire electric field and the little r is the radius of the ring. You break that down, cancel some pi's, and you get that it's equal to Q 2r delta r over big R squared. Inputting that into the previous equation, we get that dEz is equal to 1 over 2 epsilon naught times q over pi r squared times z over r squared plus z squared to the 3/2 r dr. Then we take the integral of that and we find that E, electric field in the z direction, is equal to q over a over 2 epsilon naught times 1 minus z over r squared plus z squared to the 1/2. And then using the approximation, we remember that the golf ball is very close to the charged plane and far from the edges, so these contributions don't matter. So the electric field is essentially constant in this area. So we use that approximation to say that the electric field in the z direction is approximately equal to q over a, which is the charge density, over 2 epsilon naught. So now that we have that conceptual aspect, we're going to go ahead and plug in some numbers. First thing we need to do is determine what 2 epsilon naught actually is. So we take our 4 pi epsilon naught, which is 9 times 10 to the 9th, over 2 pi. You get this big old number, which I'm not going to read, but you can see it clearly here. Take that and plug it into this equation that we had over here with the charge density of 0.56 coulombs per meter squared, and we find that the electric field is 3.909 times 10 to the negative 10th newtons per coulomb, again in the z hat direction. In order to find the force, we just multiply that by the charge of the system, and we find that the force is equal to 1.95 times 10 to the negative 8 newtons. With this positive electric field, we would expect a positive proton, a positively charged particle, to move in the positive z hat direction. Because our golf ball is negatively charged, it will move opposite to that, so it will move in the negative z hat direction.